In 11.9, we're going to look at functions as power series. Certain functions can be represented as power series, and that's useful because power series are basically polynomials of infinite length, and polynomials are useful. They're easy to do stuff with. It's very easy to take their derivatives, it's very easy to take their integrals, and so this is going to be a useful thing, especially if you take differential equations or if you take combinatorics. So we're going to look at geometric series pretty heavily here. Recall that a geometric series with the first term of a and a common ratio of r is this. It starts with a plus ar squared and so on. You can write that as the sum with n starting at 1 of ar to the n minus 1. And remember that the sum here is a over 1 minus r. We're going to use this to, given some series, to write it as a given some function, to write it as a power series. Let's start with an easy example. 1 over 1 minus x. If you look at this, the first term is a which is 1, and the ratio here is x. I'm peeling that out of here because this function here has the same form as a over 1 minus r. So our first term is 1, next term is x squared, x cubed, and so on. If I want to write that using sigma notation, that is sigma of, and I'm just going to copy from this right here. A is 1, x is, or r is x, equals 1 to infinity. So you get the sum x to the n minus 1 in going from 1 to infinity. Now you could rewrite this as x to the n going from 0 to infinity. That also works. Let's look at another example. All the examples we deal with at first are going to start out either with this form or with something close to it. So let's look at this example. Suppose we have 1 over 1 minus 2x. Okay, the only difference here is, in this case, our a is 1 and our r is 2x. So writing out the series, we get 1 plus 2x plus 4x squared every time multiplying by 2x. And to write that in sigma notation, that would be a is 1, r is 2x. So you get 2x to the n minus 1, going from 1 to infinity. Or if you prefer, n goes from 0 to infinity, and just 2x to the n. All right, let's look at another. What if we don't have a minus there? What if we have a plus? If you have 3 over 1 minus, or 1 plus x squared. All right, in this case, our first term is 3, and our ratio is negative x squared, because we could take this and rewrite it as 3 over 1 minus negative x squared, and now this is our common ratio here. So I could write this out as 3 plus, multiply that by negative x squared. So that's actually, let's make it 3 minus 3x squared plus 3x to the fourth minus 3x to the sixth, etc. All right, now this is where it comes in handy to remember this is a, or n goes from 0 this is where it's handy to remember the form a to r to the n minus 1 in going from 1 to infinity. So in this case, my a is 3, my r is minus x squared, and my n goes from 1 to infinity. And if I wanted to, I could, and this is raised to n minus 1. So I could leave it like that, or I could break it up like this. Pull that 3 out front since it doesn't have any n's on it. N goes from 1 to infinity. This minus x squared, I can break that into minus 1 to the n minus 1. X squared to the n minus 1. This x squared to the n minus 1, I could rewrite that as x to the 2n minus 2. And leave it like that. Let's do one more. Suppose we have the series x cubed over 1 minus 2x. And we want to write this as a series. Now the first term is x cubed. And the common ratio is 2x. So I could write this out as x cubed plus 2x to the fourth plus 2, or not 2 in this case, 4x to the fifth plus 8x to the sixth. Every time I'm just multiplying by 2x, and so on. Or I could jump straight to the sigma notation, and goes from 1 to infinity of a times r to the n minus 1. Now it's kind of ugly there having two x's in there, so let's expand this out. So I've got x cubed, then I've got 2 to the n minus 1, then I've got x to the n minus 1, and I can combine these together. I can combine the x's together anyway. So you get 2 to the n minus 1, and then x, when you multiply these two together, you add the powers. So this is x to the n minus 1 plus 3, so n plus 2.